Hello, and welcome to the Big Bang Kilonova Hypothesis podcast. I'm Stuart MacLean, your host. I am also the progenitor of said hypothesis. In today's episode, I'm going to be writing a letter to Roger Penrose, informing him of my hypothesis, my Big Bang Kilonova hypothesis. And the reason I'm doing this is because of the last episode that I did. In the last episode I did, we looked through this particular editorial note. So, in case you haven't seen my last episode, this editorial note by Jean-Pierre Luminet of the Astrophysics Laboratory of Marseille talks about the history of Georges Lemaître's famous 1927 paper, A Homogeneous Universe of Constant Mass and Increasing Radius, Accounting for the Radial Velocity of Extragalactic Nebulae. The galactic nebulae actually turned out to be galaxies, what they were calling island universes back in the 1920s. But there are two main things that struck me in going through that. Firstly, it reminded me of Lemaître's idea of the primeval atom. This is Georges Lemaître's original book from the 1950s by Georges Lemaître, showing this idea of the primeval atom. It was his attempt to try and explain the causal mechanism of the Big Bang in the concepts of the ideas of the 1920s, which mainly were concerned around nuclear fission, where Madame Curie had discovered this unknown property of nature called radiation. And by using those ideas, Lemaître came up with the idea of the primeval atom, where if you took all the mass of everything in the universe and put it into a single atomic nucleus, this was his primeval atom. In presenting the Big Bang Kilonova hypothesis, I use the binary merger of two neutron stars of the superverse as my causal mechanism. And a neutron star effectively can be described as being a giant atomic nucleus. And so, in effect, I'm resurrecting Lemaître's original idea of the primeval atom. And that is going to be one of the main focuses of my letter to Roger Penrose. Of course, naturally. Now, another aspect that we saw in going through this was in how it talked about the importance of crossing the finish line first. In my case, in terms of who else is thinking about this, it seems to be myself, and that's about it. After all, first, second, third, fourth on a Google search today, and that's essentially my evidence of saying, look, I've crossed the finishing line first on having this particular idea. But it's really Georges Lemaître who crossed the finishing line first. And he is the grandfather of the Big Bang Theory. And the Big Bang Theory dates from this particular paper of Georges Lemaître in 1927. But he had also, in this paper, he actually had calculated the velocities of these spiral nebula, as they're called, or galaxies. So like the Andromeda galaxy they looked at through the telescope, and it's fairly fuzzy, and they weren't sure what it was. And the idea of these island universes, like as if our Milky Way galaxy was a single universe, these island universes were also being seen, because back in the 1920s and before that, they thought the whole universe was the size of the Milky Way galaxy, and until they realized that the Milky Way galaxy is actually one galaxy in a sea of billions of other galaxies that we call the observable universe, and the observable universe inside the universe itself is what we can know and see. But he calculated this linear relationship between the velocities of galaxies and essentially what has effectively become to be known as Hubble's law and Hubble's constant, because Edwin Hubble had access to the same data, and he essentially got the lion's share of the credit, like Hubble's law, Hubble's constant, Hubble's space telescope. Not many things named after Lemaître, and it all dates down to Arthur Eddington not seeing Lemaître's letter to him saying, "Look, I've written this paper. Here's my results," and in effect, it was him who really showed that this linear expansion of the growth of the universe. It shouldn't be Hubble's law, it should be Lemaître's law. And so this is what this letter I'm writing today is about, to put its context into where it belongs. I realize I need to write a letter to Roger Penrose. And why Roger Penrose? Well, because I'm building upon his ideas of entrapped surfaces of space-time. It's not far from me. And yeah, basically the people I should be approaching are the Oxford establishment, and then after them probably the Royal Astronomers Society, and then but I haven't done it up to this point, because essentially I want to get my work good enough. But there comes a point where, look, I've got my work into such a state that is good enough to communicate the idea. It's not good enough for a peer-reviewed published paper. But in order to get those gears going, I need to write to them. So if you see me looking off to the side, I've already written what I'm going to write, but I'm going to rewrite it, and we'll go through it together. Otherwise, you're going to have me going or throughout the entire course of this podcast. So, dear Professor Penrose, or to whoever it may concern. Although I'm going to send it to the email that's listed for him, I've got a feeling that email address probably gets many emails, and if you like me just get a normal email box, you're getting spam, thousands of it, then yeah, how do you tell the difference between the diamond and the spam? But I've got a suspicion they've got someone reading through it, and then answering accordingly. So I don't expect Roger Penrose to even read this yet, but hopefully might get something. No, if I don't try, no, I'm not going to succeed anyway. So I write to you as a fractal cosmologist to illuminate the genius of Georges Lemaître's primeval atom. Just copy and paste it there because it's because of the I in Lemaître. Make sure that I don't have it on my keyboard. So, as I explained, neutron star, compact atomic, massive giant atomic nucleus. Of course, I frame it in the concepts of fractal geometry, and by doing so, by framing it in the context of fractal geometry and the Kerr metric, or more specifically Nikodem Pompolovsky's work, because his actual cosmological solution via general relativity, I'm essentially framing my fractal argument of the Big Bang, but my causal mechanism, giant atomic nucleus of the superverse, which is a neutron star of the superverse, and that is the primeval atom. But rather than nuclear fission as being the primal mechanism, it's a kilonova. Lemaître didn't know about kilonovas or neutron stars. The discovery of neutron stars was created by Fritz Zwicky, who first postulated the theoretical concept of it. But when astronomers Anthony Hewitt and Jocelyn Bell developed their radio telescope, then they heard this regular pulse beat, and these pulses came to be called pulsars, and these pulsars originate from Zwicky's description of the neutron star. So Zwicky was the first person to actually come up with the astrophysical body that we call a neutron star. But that astrophysical body is the primeval atom. But it's a primeval atom of the superverse, a binary merger of two of them, that gives rise to the kilonova, or the Big Bang Kilonova Hypothesis. But it is Georges Lemaître who first showed the expansion of the universe. Galaxies are flying apart, therefore they must have come together at a single point. And that is the thing. And that is what, I believe it was Fred Hoyle who coined the term Big Bang. He didn't use the term Big Bang. He used the term primeval atom, because that was his causal mechanism for what was actually being observed. So that's so that is what's contained in the first sentence there. It's showing them where I'm coming from. I'm a fractal cosmologist, and Georges Lemaître really was a true genius in coming up with this entire concept before even Zwicky. So, naturally, as I've already mentioned it, I assume that fractal geometry is the cosmological principle. And so there's my lens of how I'm coming at my Big Bang theory. It's also the mathematical lens I'm coming at it, how it's being framed mathematically. So right there, I'm separating it from a lot of the garbage that might come in about. Oh, I've got all these other ideas. Well, if you can't quantify it, it ain't worth nothing in physics. I'm getting close to quantifying it. I've got framework, and so that's part of the thing I need to communicate. And consequently, self-similar patterns repeat themselves irrespective of scale. So it's all about matter of scale. The superverse, a star of the superverse, is 330 million light years across, given the one in the Boites supervoid. That is my basic argument, which I first gave here. So the whole concept of the superverse, as I invented it, came from the Boites void. And in trying to think about a way of testing my idea, I don't actually have the flow of stars or galaxies around the void, but I do have the one from the local void. So this is the observed dark flow, as it is called, coming from Brent Tully's work. So, given the existence and birth of a gravitational singularity. Okay, here I'm going to put a 1. So, it's very important to make references to the papers that I'm pointing to. So I've got to make sure I've got all the references to the papers that I need. But this one is probably a very obvious one to Roger Penrose, because he was involved with it, because it comes from his friend Stephen Hawking, and it's his PhD. Because the important thing about Hawking's PhD thesis is that Hawking took the FLWR metric, rewound the clock back on it, but he applied Penrose's idea of entrapped surfaces of space-time in order to show that the Big Bang singularity, as it's called, was an actual gravitational singularity. So how do we know? So why do we say that the Big Bang has a singularity at its very beginning? It comes from Hawking's PhD thesis, which is this here. So that becomes reference 1. Of course, look, I do like who's in charge of the Cambridge University's library. The mover and shaker behind all of this, I say, is Apollo. My belief is my belief. I know what I've seen. But yeah. So, gravitational singularity, birth of a gravitational singularity, citing Hawking there. At the heart of the Big Bang theory, I to studying the pattern of birth of a knowable singularity of knowable singularities inside our universe, namely black holes. So I'm going to cite that there, but I'll also put the link in for Penrose's original paper. So I make sure I've got all my links. If you ever want to know what I was originally doing, it was turbidite research. So I learned a lot about. I learned and implemented a lot of sedimentary nonlinear dynamical processes using computational fluid dynamics to simulate effectively what are underwater avalanches, but instead of snow, it is of sediment, and these underwater avalanches flow down into the ocean and spread out, and they layer up and layer up and layer up and layer up. So I developed a full suite of software to model all of this, and including doing a GPU implementation on some of the original NVIDIA stuff. So how do I learn all about how to do the math of this? It's really coming from a lot of this. So that's where I'm coming from. I'm looking particularly for Penrose. Is that his original spacetime singularities? No, that's a lecture I did. So I'm looking for his the 1965 singularity theorem. So this is an editorial note on his original paper. I thought I talked about it. I'm just wondering about it. In his actual paper. I know where to find it. So this is the paper that really sort of cemented black holes in terms of general relativity, and it's where the whole concept of entrapped surfaces of space-time came from. And the important. So I'm just looking through the graphics here because I know how I've used this image before. So let's find it. There it is. So here's Roger Penrose's original paper dating from December 1964. I think it published in 1960. It's also published in 1965, where he shows the collapse or the collapsing core of a star, how it compresses the matter down such that there comes a point that the Lorentz transform points inwards in such a way that the only possible way the light is going to travel into the future is down towards this gravitational singularity which develops. So it shows how it's showing mathematically in the context of general relativity how the singularity is actually born. So that's the actual paper I want to reference. I can just copy its title from here. Copy, paste. 2. So hence the reason why I'm writing to Roger Penrose very specifically, because really that I am building upon this work. A subverse, our universe, and the superverses as well. They're all entrapped manifolds of space-time, like a black hole. But we're ejected out from the black hole, and the black hole effectively is like us blowing a balloon up in the room. The room around exists before you blow the balloon up, and so the superverse exists before the Big Bang Kilonova event actually occurred. And you blow the balloon up, and the black hole gives birth to a rotational white hole on the other side of the entrapped manifold, which is on the other side of the wormhole. But the wormhole itself is entrapped, and because the wormhole is entrapped, the balloon blows up, and so it's like inflating a balloon in the room, and the balloon gets bigger and expands, but the air is entrapped in the balloon. And actually, so if I go back to my general relativity and rotation, so I've done a nice animation of this analogy, because truly nobody can be uncheered with a balloon. And so the superverse first is born and blows up and inflates into the superverse, and then we've got a recursive argument. So this is where black holes are all about recursion and scaling everything down. It crushes everything. It's a big crunch down in and out into the volume of the superverse. And then in the Big Bang Kilonova event, our entrapped manifold of spacetime inflates inside the superverse and expands out into the volume of the occupying superverse. And we fall into a black hole inside our universe. We become entrapped inside our universe. A black hole inside our universe gives birth to a subverse. A subverse inflates like a balloon inside the volume of our universe, because the wormhole is entrapped. And so that's how, and we fall into the black hole of that. We travel down through the entrapped wormhole, out through the white hole, through the polar regions, and so we come out to the subverse. And so nobody can be uncheered with a balloon. So all that is justification for what I'm saying in that one single paragraph, sir. Dear Professor Penrose, or to whoever it may concern, I write to you as a fractal cosmologist to illustrate the genius of Georges Lemaître's primeval atom. Naturally, I assume that fractal geometry is the cosmological principle, and consequently self-similar patterns repeat themselves irrespective of scale. Given the existence and birth of a gravitational singularity at the heart of the Big Bang theory, I look to study the pattern of birth of a noble singular singular and plural of noble birth of noble singularities inside our universe. The pattern of birth of noble singularities inside our universe, namely black holes. So, right off the bat, why should they listen to me? Mathematical description and proper citing of their work. So, in describing myself as an independent researcher, because after all, I'm a guy who just managed to kind of put two and two together and come up with this idea, and saw no one else doing it, so I have developed my ideas for 6 years now, about the length of time I've been on this, and find no one but myself has thought about Big Bang in this way. Now, the reason I'm stating it like that is because the entire purpose of a university, entire purposes of cosmology departments and physics departments is to be looking for these ideas. So me coming along and saying that, as arrogant as it may sound to people's ears, is quite literally the truth, as far as I can see it, and the people call Google the... And so I think that's what I say and that's effectively what I say in the next sentence, meaning it's very easy to find my body of work, as if you Google Big Bang Kilonova or Big Bang Hypernova. So let me just show you Big Bang Hypernova, because I was looking at a star of the superverse. Here it is here, Big Bang Hypernova Hypothesis, which has evolved into the Big Bang Kilonova Hypothesis, given the anisotropies. But it was the Hypernova Hypothesis first, because I was thinking of it in terms of gamma ray jets, because they travel away from one another. It is a solution to CPT symmetry, as particularly pointed out by Andrea Sakharov. The theoretical consequences of quantum theory, this charge parity time symmetry, is that you have two universes, one universe of matter, one universe of antimatter. Otherwise, the two are annihilating themselves at the very beginning of time, which is what the actual currently accepted version of the Big Bang Theory says. It says that, in fact, let's have a look at that. Let's have a look at that. Baryogenesis is the key word. CERN, matter, anti. Because essentially, if we look at CERN's main mission statement, this is where it talks about this annihilation of matter and antimatter, and in it you have about 1 particle per billion actually surviving, because of a slight imbalance they found in I think it's the kaon particle, between the kaon particles of matter and the kaon particles of antimatter. They find this slight imbalance, and because it's the closest conditions to the Big Bang, I mean, it's a nice attempt, but really a much more elegant solution is this is a consequence of CPT symmetry, as first discussed by Andrei Sakharov, and it is kind of the basis for the Janus cosmological model. Or CPT. So here's the kind of main graphics, which shows us a universe of antimatter and a universe of matter. Jean-Pierre Petit, who's also from Marseille, who developed this cosmological model, puts the arrow going the other way towards the Big Crunch and then out through the Big Bang. And then there's Julian Barber's work, which says, well, this is not actually a singularity, it doesn't quite come back down. I really talk about the Big Crunch as in the Big Crunch of the superverse. So yeah, that's a wee bit of the history of the specifics of why I say Big Bang hypernova. And again, like I say, I currently hold the #1 rank for it. It is at the very top ranking. Very top of the ranking. For first, second, and third. So essentially, I really don't like saying this sort of thing. I really don't. I think it's arrogant, and it's sort of like it just turns people off. But I'm approaching Oxford University, and I'm saying something really arrogant, and then I'm justifying it. And there's my justification. So, am I arrogant? No, I'm just saying, I'm just simply stating the facts of where I am. But why? Why is my Big Bang Kilonova hypothesis hopefully these should look up. Yeah, there we go. So if we go here, as you can see, this is the large scale anisotropy map from the European Space Agency. The difference between this map and the other map that you usually see. So I think if I come back in here, so this is linked off from a page which actually gives the full cleaned map where it shows a homogeneous and isotropic universe. So it's a map that's more being developed towards the given assumption of the universe being homogeneous and isotropic, but there are these large scale fluctuations that other cosmologists are saying, oh, look, these are not a local phenomenon. These are part of the cosmic microwave background radiation. So that's what this map is. It's coming from that particular point of view. So as a fractal cosmologist, I'm rejecting the homogeneous and isotropic assumption. But it is the very nub of the argument that I get to in the next couple of paragraphs of my letter. But as you can see, got a hot spiral, cold spiral, primary evidence. This is the justification for it. And this is what I say in my next paragraph. The large scale anomalies, so I'm calling them anomalies because I'm using, and for that I'm going to link that. So because I'm calling them anomalies, Planck enhanced anomalies. Anomalies, ESA. So reference to 3 here. Identified by Planck of the CMB show 2 spiral arms in the southern hemisphere whose epicenters are the cold spot and so I put cold spot in capital letters because it is an actual feature. So this is my essay on the CMB cold spot. This is the part down here. And as you can see, it's the part circled here in the image. CMB cold spot 5.9. Here's the original publication of Planck, and it said 5.9. So if we go down to 5, here's a loop. These, oh, I love these things. Another time, talk about quantum gravities and singularities. I probably discussed it elsewhere, but it's me. Looking for 5.9. 5.9, the cold spot. Cold spot's now found in the WMAP first year, and then it's been reproduced, and that's that particular feature. So let's actually make reference to that, because we're making reference to the cold spot. So yeah, making specific reference to the cold spot there. So it's 3 and 4. And I'm making a reference to the adjacent hotspot to an adjacent hotspot. I also remember developing a particular page on my site. So I'm just looking over here to try and find the page that I'm talking about. So I do remember right. So on my front page is these author Molly Wilde's or this image is a Molly Wilde projection, and then this is where I map it back onto the sphere such that you can see these features. This particular image is what's called the best fit model coming from WMAP. Essentially, it's the best picture of the actual large scale anisotropies on their own, as opposed to having all the fine detail that exists at the much smaller scales of the cosmic web. This is the image of the universe as a whole, and so this is showing these two particular features, and it particularly shows cold spot, hot spot, and the two spiral arms. Those two spiral arms being the gravitational waves of the super kilonova event that we call the Big Bang. So that's all that evidence. But yeah, I really need to find this particular link to this particular image. Okay, so yeah, I developed this particular page, but it's actually is standard programmer to do, where I can project it onto a Molly Wilde sphere. So I was going to write. So I was basically describing how I'm presenting my data. But but for someone like Oxford University, it's a fairly straightforward thing. But so here I'm making specific reference to my front page, because that's where I have these Molly Wilde spherical projections of, firstly, the actual ESA Planck, and then of my particular best fit model showing the large scale anisotropies. Well, actually, I should say it was Jaffe who first did it, but I think it's Dr. McEwen who actually produced this particular. Dr. McEwen of Imperial University, I think that's who it was who did this particular best fit model image using what's called a Bianchi 7H model. So something for another time, going right down into the literature, but in terms of getting the best research done, that's what I've got. So next part, to an adjacent hotspot. So there's a justification for everything I'm saying right there. As the gravitational waves of a kilonova forms such a twin spiral pattern. Now, spiral pattern. I can call my proto-cosmological model, and it is a proto because I can't actually, I haven't been able to fully formulate a mathematical description of it, so, and that's why it's a hypothesis, not theory. So once I actually have that mathematical description, then we have the equation to everything. That's where this goes. That's what I'm hunting. And that equation should then describe the birth of our universe in terms of the Big Bang Kilonova theory. But for the moment, it's a hypothesis. So that's why I'm using these specific words. Meaning, I equate by the law of scale invariance and self-similarity. So these are concepts of fractal geometry. Hence why I'm stating I am a fractal cosmologist. The Big Bang to the binary merger of two neutron stars. Three, 4, and 5. And I provide a link to my own work. And specifically on that paragraph, because you usually see the map presented like that, but it's not obvious from looking at that. You need to map it onto an actual sphere, the sphere of the heavens as we see it. In order to really appreciate the twin gravitational path. I'm also saying a kilonova forms such a twin spiral pattern. Evidence. Okay. YouTube. So it's a group of physicists from I think it's Caltech that produce computer models, and these guys here are the main ones giving me. I love what they've done, because without them. But I want something specific. Videos. So trying to see who might have produced this, where exactly it's coming from. I'll present it as evidence. It's write it manually. 6. Calculation of spacetime consistent GW17104. So I think the YouTube video, I was hoping to find a little bit more info. I think I have a web page. If it still exists. I'll put in that one as well because that shows who these guys are. This SXS Collaboration. So actually, I'm going to do a little hack here. Get Notepad. Clean out some of this font. Then copy that back. And there we go. That's my hack of the day that I just made up on the spot right here and now to get rid of that get rid of the text information from copying it to the clipboard. So 4, 5, 6, 7. So I have shown twin spiral pattern. Here it is. Here's a twin spiral pattern produced by these guys. Let me see. This is the one which actually advert. So here's the actual one where it is these sort of branches coming spiraling off here that actually form that shape and twist and curve the universe in such a way, these ones here, that actually cause the large-scale anisotropies. And so that's the signature of gravitational waves. And that's what we see here. Smoking gun. That's my smoking gun. So I'll just keep that open. So, got all my links for all the justification for everything I am saying. As a neutron star can effectively be described as a giant atomic nucleus, I arrive at the idea first proposed by Georges Lemaître. In his conceptualization of the primeval atom. So, if I go back to here, I think I make very specific. I've got a So here's the actual thing from the archives, or that's the best one I could find. Primeval atom, Georges Lemaître. So reference to 8. Given the efficient packing of crystalline structures in nature, that isometric crystal lattice it's in the see crystals efficiency of packing. Okay, so to justify those words I just said there, I do like it when I'm able to back up every single word I'm saying with peer-reviewed published papers. So, do my trick again. Go into Notepad. Paste. Clear out the font information from that. Earth. I mean, in some ways what I said is I would consider it fairly evident, but I'm making a very important argument. So back it all up with do my thing again. Actually, I just probably want to write that because it's all uppercase. Backing end. Geometry. Who's doing this? XXIII. Yeah. Again. Copy, paste. There we go. That's so. Because I'm going to use the word isometric, I specifically make reference to the isometric crystal lattice, but there are all forms of packing crystals together, and if anything, a neutron star is effectively neutrons all compressed in together. And so how do they what kind of ordering do they form? The most likely form is a crystal lattice. Or there are other descriptions, like we talk about nuclear pasta, but we want a most basic description. And the most basic description is describing it as a big crystal lattice of neutrons. And this is extremely important, because the reason I'm saying what I'm saying is, well, the universe is both homogenic and isotropic, is that's the cosmological principle that needs to come down. This is me getting straight to the point of saying, look, mate, I've answered a question of physics. I've answered one of the most fundamental questions of physics. I'm doing it in 4 paragraphs. And that is the signature mark of physics. If you can say it in such short order, able to say the most and using the least amount of words. So, given the efficient packing of crystalline structures in nature, a very basic description of neutron degenerate matter of a neutron star would be to describe it as a regular crystallized lattice. In addition, each neutron on the lattice is exactly the same as every other neutron, thus giving my model initial conditions which are both homogeneous isotropic. And there I make reference to 8, 9, and 10. 8, 9, 10. Let's see. I mean, that's how I mean, there's many main descriptions of what a neutron star is, but there we go. And it's Harvard that's saying it. It's not just me saying it. The result is a tiny star that is like a gigantic nucleus and has no empty space. Thank you very much, Chandra X-Ray, for saying that so eloquently for me. So, I'm not the only astronomer saying it. It's Harvard that is also saying it. This thing again. And the Chandra, this mission has been, this is probably Chandra, Fermi, Swift. There's been various X-ray and gamma ray telescopes, and they have been an absolute blessing for me. They produce the best, the very best. They really have produced. They have really given me all the things I need to do this observatory. 11. That's very satisfying. So I'm pretty happy with that. With the first 4 paragraphs. First paragraph essentially showing where I'm coming from as a fractal cosmologist, and thus showing my with my mathematical and philosophical lens by which I'm coming about my idea, which is essentially to say, look at the birth of knowable singularities, i.e., black holes, inside our universe, to talk about the actual birth of our own universe. Then, in the second paragraph, I introduce who I am, how long I've been doing this, but more importantly, why should they take me seriously? Well, given that universities and institutions are dedicated to trying to find out and come up with these scientific explanations, i.e., the Big Bang theory, I actually hold some very keyword positions, and it is my work at the top of the Google rankings. So, saying how do you know something, or just Google it? Well, it's my work, and this. Why? That's really introduce myself. But then in the third paragraph, I give my smoking gun evidence, straight up with the microwave background radiation, and identifying it as a kilonova event by its very signature. Hence, that's my smoking gun. Then, in the fourth paragraph, this is where I actually managed to do what I guess most people call real physics. And it comes down to this: the cosmological principle. What currently is considered the cosmological principle. And it's this: that the spatial distribution of matter in the universe is homogeneous and isotropic. Why? Up to now, it's always been an assumption. No one's actually answered the question, why is the universe homogeneous and isotropic? And in the fourth paragraph, I give reason by simple naming. A kilonova is a binary merger of two neutron stars, and a neutron star is effectively Georges Lemaître's primeval atom. And so I am most showing up, and thus I justify my very first sentence to illustrate the genius of Georges Lemaître. So with that said, I particularly So now to give my idea some context. So to give context, I employ your ideas about entrapped manifolds of spacetime via the Kerr metric as rotation is a critical component of the pattern of a kilonova and hypernova. So here I am actually addressing Penrose directly and saying "your," and from that 1965 paper. Which one? Is this the one we saw earlier? Unfortunately, I've gone and lost it. Here we are. So, making specific reference back to this paper. So yeah, that is right in referencing his paper, because he starts as this Schwarzschild, and then there's the newly discovered Kerr metric, and essentially I specifically make reference to, it's in the diagram here. These are Penrose diagrams, and it's this particular essay here, general relativity and rotation, that I really made the link. But here I was actually still thinking of hypernova. It was the Big Bang hypernova, so I've kept the banner at the back, because at that point it was the hypernova. And I built up a description describing Penrose space-time diagrams and the ideas of entrapped manifolds of space-time, which is best illustrated here, and the path of travel of causality through here. The causality gets really broken up here. So that's why I specifically say via the Kerr metric, as the rotation is a critical component of the pattern of a kilonova and hypernova. It's here I'm making a link. But it was after writing this part here, I'm thinking about these, and that's when I came up with the Big Bang Kilonova Hypothesis, really more or less straight after this essay, and then I went into full production of presenting what is essentially now my main thesis, or part one of it. The second part we'll talk about in these podcasts, and we'll see it come together as it comes along. But at the moment we're doing more physics and getting the important things done in physics, which is writing this letter. More recently, and this is part of the new work I'm talking about, I am looking at Nico Popolomski. So he's a Polish theoretical physicist who's developed a Einstein-Cartan formulation of GR. I'll just use abbreviations here. GR being general relativity, in how he maps the FLWR. So that's the Friedman, Lemaître, Walker, Robertson metric, the history of which we discussed in the previous episode. And this is important to say it because the Kerr metric is a local metric. It's good for describing something like a solar system, the space-time curvature within a solar system, or within a few astrophysical bodies. It's not good for describing the universe as a whole and the distribution of mass throughout the entire universe. So that's what the FLWR metric is. It's a cosmological metric. So, and when you say metric solution, essentially it's a bunch of equations that, when differentiated, equals the differential equation that is general relativity, or the set of 10 differential equations that form the core of general relativity. So also, so Nikodem Pompolanski, let's get his work up. So come. So this is Nikodem Pompolanski's paper, Universe in a Black Hole with Spin and Torsion. So the way the Einstein-Cartan formulation of general relativity works is that it's got this thing called a torsion metric, and as the neutron star or the kilonova collapses down into a ring, which becomes the ringularity, this point of infinite curvature, rather than actually fully collapsing down to infinity, I would say there is this degenerative pressure that comes back, that arises from the torsion, and from the Einstein-Cartan formulation that arises from the torsion metric, and what creates what Pompolanski calls a non-singular bounce. So it stops the equations blowing up to infinity. So it's so we're getting rid of any kind of like paradoxical infinite points of curvature from finite mass, and which is I think is, how can you have a point of infinite curvature which is finite in mass? Doesn't. But more importantly, it is actually, it's the one that's describing a universe in the black hole, i.e. it's the FLWR metric mapping into the coordinate system of a black hole, given this particular Einstein-Cartan formulation. I spent quite a lot of the beginning of this year thinking about this, quite a lot about the torsion metric. If I can describe if I could give a mathematical description to what I'm going to be building upon, Nikodem Pompolanski's work is the closest I found to it, given all these various factors I'm talking about, and he's also describing in the he's managed to get it as his idea as a full cosmological model. The difference between what he's saying and I'm saying is, one is I'm giving a cause for why the black hole is born, context to where that black hole is born, i.e. in the superverse. My descriptions are coming from fractal geometry, and I recognize that the wormhole is entrapped, rather than, say, going through a higher dimensional bulk, as it were. So I'm particularly using the phrase of the film Interstellar when talking about bulk. So that forms reference 12. And it's important to say it because this is my mathematical framework that I'm coming from. I'll do my notepad trick. It removes the font information from copy and paste. Okay. So, yes, actually I do want to Penrose 1st of December 24. So, citing 12. So there's a point about mapping a cosmological metric in, so it becomes an actual cosmological model. accounts for, but there is the other point about rotation, because rather than a singularity clamping down to a point of infinite curvature, it's spun out into a ringularity, which thus opens up a wormhole. But rather than a traditional wormhole, which traverses, is seen as a doorway to someplace completely imaginary, this wormhole is entrapped. And why wouldn't it be? When the wormhole is born. So let me just bring up Penrose's find it again. So many papers, so many referencing. Actually, I'll just find it for my reference here. So if I find it, Planck anomalies, so it starts my search from there. Penrose. Ah yes, there we are. Gravitational collapse. So, as the star collapses down on itself, or in the case of Kilonova, two spin around each other, they tear each other apart. And I'm going to do some brilliant artwork for showing this, for showing how different parts become entrapped. So in a ringularity, you've got the inside, then you've got the outside, and all that presses down, and so it creates. So here's the top of the universe. It dips down towards the ringularity, around it, and then back up. And this piece up here, this new part, that's the start of the balloon, or more like blowing bubble gum. You starts off small and it gets blown up because it is in itself entrapped and weighed down, or effectively the ringularity is the anchor of the universe. It is the in the balloon you've got the mouthpiece, that little rubber ring mouthpiece. That's the ringularity into which you blow and everything inflates. But it is essentially entrapped down there, rather than, say, going through imaginary higher dimensions, of which we have found no evidence from experiments that have been carried out by the CERN. So this is why this explanation works so well in saying in inventing the superverse. And I get my picture of superverses and subverses from fractal geometry. So if I look at a Mandelbrot set, so let's see a Mandelbrot set, particularly the Mandelbrot set zoom. So we just open this one here. As we go down further and further, self-similarity happens irrespective of scale. And so you see these points in here which are the Mandelbrot set being reproduced. Here, in the very center of these, here it is. Here comes the Mandelbrot set again, at such a smaller scale. So by pointing to an object of the superverse and saying, okay, that's a star, by saying we inherit our fields. So everything about our universe we inherit from our parent universe, and everything about subverse it inherits from our universe. Thus, self-similar patterns repeat themselves recursively. So this is why I'm always framing it in terms of fractal geometry. In fact, it took me about 3 years just to kind of come up with the principle of like saying fractal geometry is the cosmological principle, and then learning to work by that and what that exactly means. So everything I take is a description of a kilonova. I'm taking everything from nature, looking at it, saying, how is nature giving birth to a gravitational singularity in order to describe how the Big Bang happened? And it does surprise me that no one has actually made that particular argument. So, hope that doesn't raise any copyright strikes on YouTube by doing that. Otherwise, if it does, I'll replace it with one of my own. Actually, I could probably ask my brother who does. He was the one that did the Mandelbrot set as a kid. Like Popolonsky, I also make reference to the Planck evidence for a closed universe. Okie dokie. That last sentence, I'm writing from memory because was it this paper? So let's think. Let me think. I'm looking for So I looked for Pompolanski's paper, which is probably right at the end here. I need to bring up my website because I linked to a very, very specific paper about the universe being closed. So that's one of the papers I'm going to need. The universe is flat. So the universe is flat because that is the shape of the superverse into which our universe is inflating. So as if you're inflating a balloon, the curvature of the room is mostly flat, okay, given the slight curvature of Earth. But if you're doing it aboard, say if you do it aboard the International Space Station, that'd be more cleaner of being in a microgravity environment. The space there is flat, and because it is flat and you blow the balloon up, the balloon itself is not being deformed by any warp curvature in space-time. It's Minkowski space-time. It's flat. But the one I'm looking for is that the universe looks like it's probably enclosed by data from the Planck Commission. I think I probably have it in my main thesis. So, Planck, thickest two large Plancks, Planck. Here we are. Measurement of the universe flat and closed. Reference 70. So here's my evidence for saying that the universe is enclosed. So some new references. 13. Just copy and paste that. And then, so that particular paper, or those particular papers, So, quoting Nature here. Copy that link right in as well. So, Planck evidence for a closed universe and a possible crisis for cosmology. Not for me, it ain't. Crisis? What crisis? Oh yeah, but then again, at the moment I'm the only one doing this, so, but a flat universe. I'm going to do my notepad trick again. Copy the names in. So many people involved in so this is the actual shape and structure of the universe as it is measured from the cosmic microwave background radiation. So again, primary evidence. So if I go ahead and copy that other link in. So again, the importance of this so the other one is you need to make sure that Popolonsky actually makes reference to this paper, because I'm going by memory. Actually, let me just close down some of these tabs, as we've got links to all of them. Clean up things a wee bit. If I need them, I can just open them up again. I've got a reference. So we'll talk about that one, and I want that one open. Because this is the shape of the universe as measured by the cosmic microwave background radiation. I think the keyword being closed. Going new closed universe with a three-dimensional analog of a sphere. Let's search for that. Actually, if we just search that and Popolonsky's name. So that's the actual paper itself. Let's include Popolonsky. Yeah, that's the one. Gravitational collapse. Planck evidence for a closed universe. So yeah, that's a reference to one that where he is actually making reference to the same paper that I'm looking at, saying that the universe is for arguing a case that the universe is closed. It is actually, in fact, an entrapped manifold of spacetime. So that's the particular paper I want. So 2, 12, 13 and 15. 13, 15. So there's all my justification for my 5th paragraph. Next, however, this wormhole is entrapped inside black hole. So why do we assume it goes anywhere? So that's saying a star collapsed down, or the ringularity is created from the debris of as the 2 neutron stars shatter each other apart or shred each other apart. A ringularity forms which collapses down below the critical point, where the critical point being the point where the event horizon is born. But then you've got the entrapped surface of space-time inside the ringularity that in itself in turn inflates and becomes the entrapped manifold of space-time that is our universe. So that's, but yet everyone assumes, well, it's going someplace, somewhere else, and there's been more imagination put into the idea of the Big Bang than actually taking any actual lesson from nature. I'm able to do this because I'm not an expert in kilonovas by any measure or means. In fact, many of the podcasts we're going to be doing, I'm going to be learning about kilonovas as I read them to you. But yeah, hello Oxford University. I find myself in this awkward position. Here, I introduce the idea of the entrapped wormhole and recognize that in the polar regions of a given rotational black hole, there are 2 entrapped manifolds inflating inside a given universe. Now, of course, if you want to see all that along with everything else, go ahead, watch my film here. I've animated it in every kind of detail way, so that's how I picture it in my imagination, and enjoy. And one of the key arguments I make is about Fermi bubbles. So I go down to Fermi bubbles because I'm going to need to reference them. Inside ours saga A star, being the supermassive black hole at the center of our own Milky Way galaxy, has ripped the fabric of the electromagnetic field to create 2 entrapped balloon manifolds which grow, which not glow. Let's talk about Fermi bubbles in the gamma ray light. Fermi bubbles. So that's also got Fermi bubbles. So spotted by NASA Chandra X-ray. These very large cloud. So this is the Milky Way galaxy running along here, and these are these large cloud formations, or large ghost-like formations, because they are completely invisible to us, but glow in the gamma rays. So when a hypernova inside a subverse occurs, that causes a reaction large enough to create high energy reaction on the electromagnetic field inside our universe, and so matter that has been gone into the black hole and been injected out into the subverse, it's ejected out into the entrapped manifold of space-time around the entrapped manifold of space-time that are the two subverses, i.e. these two balloon things which glow in the gamma ray. And they're glowing because events inside those high energy events like kilonovas or hypernovas inside the subverse happen, and they cause cause a high energy event on the gravitational field of the given universe, i.e. the subverse, and that is to us the electromagnetic field. And so two high energy gamma ray photons, or like two high energy gamma ray bursts in our universe, would be super photons in the superverse. But so that's how I am answering the black hole information paradox. In a sense, that's the best on the spot explanation I can give of it. Another mystery solved. That's the beauty of this. It just keeps going and going and going. So, Fermi bubbles. That's how I account for Fermi bubbles. Fermi bubbles. Fermi telescope. NASA. So that's 16, and it's also, and I also reference 5 because that's where I'm giving this argument, and I present, and also I present the argument that these large balloon manifolds of entrapped space-time that are completely invisible to us, but do have mass. Well, that's dark matter. I think that's one of the arguments that I'm trying to go for here. Yes, in the next paragraph. So in effect, this letter is what is becoming. I'm setting it up as what I call the broadside. I'm looking at Einstein, and he released a series of four papers, which then gave birth to quantum mechanics, quantum mechanics, starting with special relativity, which then became general relativity, But these four papers fundamentally changed the whole course and nature of physics. Fractal geometry is the cosmological principle. What's your part going to be? What's your part going to be? But the broadside is basically a naval term of like, the ship comes in and unleashes the cannon fire on it, and that's what I have to do here. It's essentially, look, I'm going to, one simple idea, I can do all of this instead of having to have lots of different ideas that don't quite coherently come together, like dark flow, which I'll talk about in a second. But first, this paragraph. However, this wormhole is entrapped inside of the... Oh, right. Yes, I didn't quite complete this one. Thus, I define a subverse and origin story of dark matter, as well as explaining why no particle has yet been found. Now, some of you may be crying axiom, axiom, axiom. I think there's been a very big misunderstanding about what the nature of particles is, and what's inside a particle, and what it is to be inside the one electron universe. And the evidence I will throw down there is... that's where things get really interesting. But no particle of dark matter. I'm wanting to justify it. You may scream axiom, axiom, axiom. Big think. Well, everything starts with bang. It's best. It does. I mean, there is no specific paper that says there cannot be any particle of dark matter, particularly when everyone's thinking that everything is made of particles. Particles are vibrations upon a field, but what is that field? What's its anatomy? That's why I do the big think. Dark energy dominates. Oh yes, right. So yeah. To answer the... So that's 17. Bit lowering my standard in references. I prefer papers, but in just generally making a point about dark matter and dark energy, they're just trying to balance the equations in order to use what is existing in terms of existing mathematical frameworks without having to rethink everything through from the ground up. Fractal geometry is the cosmological principle, and it's been my pleasure and eternal gratitude to do that thinking. I mean, I love this stuff. And seeing Borges is written in a rather strange way. It's got a particular accent over it. Where it is. so I have the accent. Seeing the more spherical void of dark energy at a diameter of 300 million light years and a star of the superverse. So I'm going to back that up with what I've been showing you here. So this is this essentially was the Big Bang Hypernova Hypothesis as I first put it forward in 2018. So copy that accent of the laboratories void. So I'm referencing my exact piece of work because it also contains the main primary bit of evidence that I'm going to show. So dark energy is that mass energy density that belongs to the superverse that is not part of our entrapped manifold of spacetime. So an object exists in the path of where our universe is expanding into, just like a stone exists in the river and it flows around it. And so our universe flows around it. And the observational data that shows that our galaxy is actually flowing around voids like the local void, but I also expected the same to be for the laboratories void. So there's a prediction, a way of testing my hypothesis right there. But this is the local void, so these measurements are going to be way more accurate than the laboratories void, because this is in the local group. This is our Milky Way galaxy. We are here, and these are the surrounding galaxies. And on the other side of the Milky Way, invisible from us, there is this massive void that Brent Tartully has mapped. So I'm just going to copy that because I know I'm going to use that as a reference. Again, provide observational data, observational. Brent Tully. Another reason for saying flow is that I remember seeing somewhere that the equations of general relativity, an exact solution to the equations of general relativity are the equations that describe the perfect fluid, i.e. a fluid without viscosity, like liquid helium. In fact, I think there's a lot of things that liquid helium does that are very, very magical, like producing frame dragging in a lab, for one, and I just see warp drive and jump drive in there. That's interstellar space travel, that's what I see. But instead of going off on a tangent, yes, coming back to this paragraph. So I talk about larger parent universe, that which call the superverse, that which I call the superverse, that which I call the superverse, because using I'm trying to say, I use set theory in the description of my name, subset, superset. So this is where this nomenclature, this is where this is why I name these words. And these are the words I make up. Superverse and subverse. And the two simplest words I can make up to describe what is beyond the bounds of our universe, and in the context of what a black hole does inside our universe, and in context of describing the Big Bang and how it came to be. And all of this done framed in the concepts of fractal geometry. So I'm trying to find the least words here to say parent universe. Boring set theory. Boring. Following set theory. The larger parent universe following set theory I call the superverse. So yeah, that describes what I'm talking about subset, superset. That comes about through the laws of self-similarity and scale invariance. So how am I reaching the concept of the superverse? Seeing an object of the superverse as a big sphere. Fractal geometry says that patterns repeat irrespective of scale. So a big enough star of the superverse that's big enough to give birth, that holds enough matter or energy that it gives birth to our universe. There is also a whole lot. There is a point of why would we call it energy? I mean, it is mass energy density that belongs to the superverse, but to our perspective, it is energy, as from our perspectives, from the perspective of the observer inside the superverse, and looking at our universe, we would see our universe as energy, whereas we see it as mass. That particular lexical, that's the best way I think I can phrase dark energy, dark matter in terms of how each one perceives the other. So we would perceive the subverse as pure energy to us, but if we're inside a subverse and we're looking at a subverse of the subverse, the matter of the subverse would have mass to us, but something entrapped within the subverse would have mass. I think I'm kind of making this up on the spot as I go. So great thing about this podcast, you never know. We just do a little bit of history and then probably give birth to entire new science while doing it. Oh yes, we'll talk about the grill in a second. Talk about theological nightmares. Well, for me it is. I don't know. I just get dumped straight into this and get both barrels in the face by life, the universe, and everything. I'm just sharing. In equating to inflating a balloon, our universe expands inside the larger superverse, which is itself mostly flat. hence why the universe is flat as seen from the CMB. So back to that paper 14. 14. Numerical order them. 14. So I make 18 should be my reference, and I make reference to 19. Actually, I make reference to 19 in the next paragraph, really. In defining dark energy, so reference to 5, because that's where I give my definition of it, as that mass energy density belonging to the surrounding superverse. I give it capitals. I call it superverse or a capital letter because it's our parent universe, and so I give it a bigger letter. It's bigger than our universe, so it has to start with a capital letter. And to us, there is only one parent universe, the superverse, into which our universe is expanding. I make the I'm not liking that too much. Belonging to the surrounding superverse, but is separate from our I mean, it flows around it, but it's not mass, energy, and density that belongs to our universe because it was not part of the Big Bang. So I need to make specific reference to a measure of dark energy, dark matter at the time of the Big Bang and compared to now. And dark energy. That's one. That's the pie chart. 9-year mat. So let's make a reference to that. See, here today it's mostly dark energy, but because our universe hadn't expanded out into the universe. So I'm thinking about turbidite flows here as end of flow, and flows out, and it flows around existing obstacles that are there, and then envelops them. And so that's how dark an object that's composed of dark energy to us, which is mass, energy, density, belongs to the superverse. So that's what I'm referencing there. Content of the universe pie chart. W map 9-year. 9 years. In defining dark energy as that mass, energy, density belonging to the superverse, into which our universe is expanding, but not causally, but causally separated. I say causally because of the geometry of causality. The only way to get geometry of causality is through the black hole, out through the white hole, out into our universe. And it's not possible to go backwards. You can't travel back through the white hole. And there's only ever one white hole per universe, the one that gave birth to it. All other white holes inside that given universe are causally disconnected because it's on the other side of the black hole where there's the giving birth to the balloon manifold of spacetime, into which our universe is expanding, but is causally disconnected. So I'm particularly talking about the geometry of causality here and its disconnection. But the two actually can coexist in the same place. And one of the reasons why I equated the electromagnetic field of the superverse to our gravitational field was because I cannot put my hand through my phone. It's solid. My phone is solid. I cannot put my hand through my desk. But yet most of the space in between atoms is free space. It is only because of the electromagnetic field and the repulsion of electrons versus electrons that gives an object the property of solidity. So in seeing the solidity of the superverse in terms of its electromagnetic field being our gravitational field, that gave me this description of talking about electromagnetic fields of given particular universes, and it's where I've been concentrating most of my ideas this year in understanding exactly what I'm saying about these entrapped manifolds of spacetime and what evidence there exists to back that up in terms of fractal geometry, in terms of nonlinear dynamics. Well, when you get close to a neutron star, you're getting to an electromagnetic field or electromagnetic field of a black hole is so strong that it's some of the strongest in the universe. Magnetars are the strongest magnets in the universe. These are particular types of neutron stars. And because it is above the Schwimmer limit, this particular limit here, because the electromagnetic field, the strength of it is above this particular limit, the Maxwell equations of quantum electrodynamics stop becoming linear and become nonlinear. So we have nonlinear dynamics of a field within inside the neutron star. So in terms of trying to give description as to why the fields are being torn apart, why I'm saying electromagnetic fields forming two subverses inside our universe and why it's being torn apart. This is where this description is coming from, and it's where I'm starting to get into the ideas of Stephen Hawking and Hawking radiation. But I've already given an answer to the black hole information paradox by way of Fermi bubbles. So that's dark energy. And writing this, so back to writing this one sentence. In defining dark energy as that mass energy density belonging to the surrounding superverse, into which our universe is expanding, but it's causally disconnected. I make the prediction. Spelled wrong. Make the prediction that galaxies should thus flow around them like the star of the superverse in the Boites. Star of superverse that is to us the Boites void. Like in a manner like in the way water flows around a stone in the river. So the river is our universe. The object of the superverse is a stone, and so from the point of view of the water, there is a void in the stone where the stone actually exists, and that is the Boites void. And so, yes, I reference 19, reference 5, I need to reference 18 again, because that is where I specifically make these arguments and present the observational data from Brent R. Tully. This and so here's where I differentiate and make a testable prediction versus the Lambda CDM model. So again, testing my idea. And the proof of the test, flowing around the river, that's the proof of the test. That's observational. Though I should just show the explanation for this particular phenomenon, according to the Lambda CDM, is that it is the gravitational attraction towards the shapely cluster, which we can't really see to it. So we're sort of moving in towards the direction of the hydra and the shapely concentration. So it's concentrated on here. So that's where the flow of the jet is actually moving towards. But I'm saying it's the flow of the universe as a whole, whereas dark flow is more saying it's a flow of the local galaxy group, because of a great gravitational attraction that's beyond our current sight. So I just want to tell you. So wondering if Brent Tully's name was associated, but that's the alternative to that observation. But I'm more specifically saying this in opposition to inflation theory. So essentially, what is my hypothesis going up against, and what is it trying to replace? Basically, I'm trying to say the minimal amount, and the minimal amount I need to just take out of everything that exists is inflation theory. And inflation theory doesn't even try to attempt to answer the question, why is the universe homogeneous and isotropic? Which we've already answered. Okay, so this is an opposition to inflation theory, where a void grows as an expanding soap bubble and merge together. Okay. New search, dark energy, soap bubble. Now I'm just going to reference my stuff because Georges Lemaître cluster. So I'm trying to find. Bourne's void and CDM. So there's particular voids in the universe. I think, was this it? Study the formation and evolution of voids and using various simulations. Called dark matter universe. We identify voids by requiring them to be spherical, elliptical, or regions. The void rescaled mass profile. So that might be one paper. Dark energy, soap bubble. Soap bubbles as galaxies and filaments. But I'm more interested. Yes, searching dark energy voids is void. Energy. There was a particular, I think it might be referenced in here, that I particularly looked at, spongy universe. So, yeah, found it. Cosmic voids, much ado about nothing. So this is one of the primary ones I particularly so this is how it's seen. So this particular simulation is showing the formation of a supervoid like Boötes as it grows and grows and grows. And so like an air pocket and bread that's being cooked in the oven, the air pocket grows and grows and grows until it becomes a big hole in the middle of the bread. As I say, that's how the landed CDM model describes the formation of the formation and accumulation of dark energy within our universe, and that is what I'm opposing here. So I'm going to do some links here because this is my opposition that I particularly make reference to in my early work, because were these from the Boötes? Because it's specifically making reference to Boötes, and there was a time when Boötes posed a threat, because how did these voids form? It would take these voids so long to form that length of time they'll take to form is greater than the age of the universe. So that caused a panic in cosmology, and this is why it's called much ado about nothing, because he's saying these voids come together in short enough time because of the accumulation of dark energy. Who was it that wrote this? You got make sure he actually exists. Okay. Yeah, same web address. So it's this guy here. Make sure I get. Want to make sure I get make sure I get the names of the people I'm whose work I'm referencing correct and everything. Do my font thing again. Word. Okay. And there was some there about. So I want to make another reference to that one because that's more general. Yes, particularly talking about the kind of the soup bubble model. That is the current explanation. They call themselves Science 2.0, and it's by the new staff. Okay, so it's no one particular person. Okay, so that gives me some links for justifying what I'm saying there in defining dark energy. That's 5, 18, 19, 21 and 22. What was 20? Yep, 20, 21, 22. Because I'm also saying I also want to put in a word here like so as our universe expands, it is thus infused with the mass energy density of the surrounding superverse, hence the reason for why there is no dark energy at the time of the last CMB last scattering. The last scattering is where the photons of the microwave background radiation actually started traveling across the universe as it went from being opaque to being translucent, because electrons bound with protons when the plasma cooled enough such that the universe became translucent and photons could begin their journey. And that's the time of the last scattering, as opposed to today. So that's specifically reference to number 20. And so in a single paragraph, I basically debunk inflation theory, provide evidence for it, along with a very simple argument to say, dark energy, mass energy density of the superverse that belongs to the surrounding superverse, which is separate from our entrapped manifold of spacetime that is our universe. So a very important paragraph, as they all are. And then to finish things off, quantum mechanics, CPT symmetry, which means I need to make a new link. And I particularly point to this episode here. And I did it in a series of chapters. I have created links in here, but I haven't actually gone through and created a reference for them yet. If I get time, I'll probably come back to it at some point. So, but CPT symmetry in the superverse. Notepad again. So this is the argument I present here. So this is really probably what I would say started the whole thing. This observation of gamma ray jet traveling away and another gamma ray jet traveling in the opposite direction. So that's where I started in all of this. And the great thing about the Big Bang Kilonova Hypothesis is that it is the hypothesis that just keeps on giving and giving and giving and giving and giving. It just renders answer after answer after answer, including why CPT symmetry is CPT symmetry, charge parity time symmetry. And to my case, so that's 23. But so here I'm time to start wrapping up, but hopefully it is enough to convince you that given I am the only one looking at this, given my Google rank. Actually, let's do that. I've already proved that point. It is at the very least worthy of consideration. So from my perspective, I would say I've already won for all the reasons that I've just laid out throughout writing this. But here's where I add the twist, just that little twist that only the true hypothesis of the universe, the true story of the universe can actually do. Because self-similar patterns repeat themselves irrespective of scale. So though in terms of the universe being a fractal pattern and consequently life and us. So an argument I give my CPT symmetry superverse about DNA and helical spiral patterns. And then cosmological. In this particular episode, so you've got these particular spiral patterns. This is the picture of the interior of the Milky Way. This is looking towards the Sagittarius A star supermassive black hole, and we see that the galactic core is full of these spiral-like patterns going from, I'm guessing, either pulsars, black holes, or new newborn stars. Newborn stars produce astrophysical jets when they are just born. So, and that pattern of one helical spiral or two double helix DNA, RNA, we are part of that fractal pattern. It is the very, 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 it's encoded into us at every level, the quantum level, at the informational level of DNA, RNA, and then right up into our myths, our legends, our religion. And this is what I'm rounding off with, though in a way that doesn't make them go, oh my god, the guy's gone crazy. But lie and are that. So I have to give a philosophical basis for it instead of terms of what might be considered Ptolemaic astronomy or astrology, the signs of the zodiac. So, though in terms of the universe being a fractal pattern, and consequently life and us are of that complex. Consequently, life and us arise from the complexity of the pattern. There is a consequence. There are. So I'm talking about there are consequences. Yeah, that one consequence being that it took, well, no. It exists. I just find the universe as it is. Oh, I just got to do this one part. See that little part in there? That's the encoding of the octal map. So it's got 6 particular closed, 6 standing waves. So that's ignition after it's passed through the actual ringularity itself, which is happening down in superverse, black hole, wormhole, white hole. So it's happening in this layer here. Sorry, we're just, so yeah, that. I will just put this up and begin explaining the birth of our universe. And the guy who was found in this box, well, he nailed up this guy whose birthday, who's just coming around again, and in 25 days it's going to be Christmas. So, consequences. Try living through the consequences. When I say both barrels on the face, I meant it. But life just has that way. An objective one at least, because this is subjective as you can see. But a kilonova is the true philosopher's stone in accounting for the baryogenesis of gold, and I have the grail. Well, actually, Tel Aviv the University of Tel Aviv and the associated archaeological institutions that inside that of Israel. That's where the physical objects are to be found, and I make reference to them via Simka Jakovich's in particular episode here where he shows this particular piece and shows the archaeological records of this piece. So this is a product of science by science. And then there's all the stuff that happened along my route to discovery. So I'm going to make a reference to that one there, because nothing, in my opinion, communicates it as this piece here. And so important is that piece that I actually make it my basic symbol of how I communicate it. It's my prime logo that I make it. That's how much weight I put in behind it. Why Saturn? Gods of capitalism, I guess. Meet the hippie sun. That, on the other hand, is that's where things get a lot more complicated than even I would like to get it, and it's my imagination. But I'll probably witter on and discover what colour of underwear God actually has. I think it's pink today. So, and I have a grail. So, 23, 24. Because at the end of the day, the theory of everything should come like a bolt of lightning. And all I can do is communicate it. The reason I put so much effort into it is because I believe I have to stand in front of God in judgment and say, look, you gave me the keys to your kingdom. I did what I could do as a human. And that's quite a lot. So I think the next part will conclude by proofreading through this, and then I'll email it to Penrose and various department heads at Oxford University. I think I've got a few others on my list that I probably want to try and do, but I think I'll do them one at a time to allow time for response to see. So I've got time to reply instead of well, let's see what happens. Okie dokie. So now that we've got our letter written, let's read it through and make sure it's all grammatically correct and makes sense. So, dear Professor Penrose, or to whoever it may concern, I write to you as a fractal cosmologist to illustrate the genius of Georges Lemaître's primeval atom. Naturally, I assume that fractal geometry is the cosmological principle, and consequently self-similar patterns repeat themselves irrespective of scale. Given the existence and birth of a gravitational singularity at the heart of the Big Bang theory, I look to studying the pattern of birth of notable singularities inside our universe, namely black holes. As an independent researcher, I have developed my ideas for 6 years now, and find no one but myself has thought about the Big Bang in this way, meaning it's very easy to find my body of work, as if you Google Big Bang Kilonova or Big Bang Hypernova, it is at the very top of the ranking, first, second and third, hence why I say this. The large-scale anomalies identified by Planck of the CMB showed two spiral arms in the southern hemisphere whose epicenters are the cold spot and an adjacent hot spot. As the gravitational waves of a kilonova form such a twin spiral pattern, I have come to call my proto-cosmological model the Big Bang Kilonova Hypothesis, meaning I equate, by the law of scale invariance and self-similarity, the Big Bang to the binary merger of two neutron stars. As a neutron star can effectively be described as a giant atomic nucleus, I arrive at the idea first proposed by Georges Lemaître in his conceptualization of the primeval atom. Given the efficient packing of crystalline structures in nature, a very basic description of neutron degenerate matter would be to describe it as a regular crystallized lattice. In addition, each neutron on the lattice is exactly the same as every other neutron. Thus, given my model, initial conditions, which are both homogeneous and isotropic. To give context, I employ your ideas about entrapped manifolds of spacetime via the Kerr metric, as rotation is a critical component of the pattern of a kilonova and a hypernova. More recently, I am looking at Nikodem Pompolonsky's work, Pompolonsky's use of an Einstein-Cartan formulation of GR in how he maps the FLWR metric to the interior of a black hole. As Pompolonsky's work accounts for rotation, that gives rise to the wormhole. Like Pompolonsky, I also make reference to the Planck evidence of a closed universe. However, this wormhole is entrapped inside the black hole. So why do we assume it goes anywhere? Here I introduce the idea of the entrapped wormhole and recognize that in the polar regions of a given rotational black hole, there are two entrapped manifolds inflating inside a given universe. Inside ours, Sagittarius A, Saga A star, has ripped the fabric of the electromagnetic field to create two entrapped balloon manifolds which glow in the gamma ray light, Fermi bubbles. Thus I define a subverse and an origin story of dark matter, as well as explaining why no particle has yet been found. In seeing the Boites void, spherical void of dark energy at a diameter of 330 million light years, I had my star of the superverse, the larger parent universe, following set theory I call the superverse, that comes about through the laws of self-similarity and scale invariance. In equating to inflating a balloon, our universe expands inside the larger superverse, which is itself mostly flat, hence why the universe is flat as seen from the CMB. In defining dark energy as that mass energy density belonging to the surrounding superverse into which our universe is expanding but is causally disconnected, I make the prediction that galaxies should thus flow around them, like the star of the superverse, that is to us the Boites void, in the way water flows around a stone in a river. This is in opposition to inflation theory, where a void grows as an expanding soap bubble This is in opposition to inflation theory, where a void grows as an expanding soap bubble which then merge together. So grows as a set of expanding soap bubbles, which then merge together to form the supervoid. This is in opposition to inflation theory, where a void grows as a set of expanding soap bubbles, which then merge together to form the supervoid. As our universe expands, it is thus infused with the mass energy density of the surrounding superverse, hence the reason for why there is no dark energy at the time of the CMB last scattering, as opposed to today of the last scattering of the CMB. I think that should be last scattering of the, as opposed to today. Of course, I have many more arguments, such as CPT symmetry, which add to my case, but hopefully it is enough to convince you that I am the only one looking at this. But hopefully it is enough to convince you that given I am the only one looking at this, it is at the very least worthy of consideration. Though in terms of the universe being a fractal pattern and consequently life, and us arising from the complexity of the pattern, there are consequences. One consequence, and an objective one at least, is that a kilonova is the true philosopher's stone in accounting for baryogenesis of gold, and I have the grail. Yours sincerely, Stuart MacLean, followed by all the various links. So, I'll get that sent off in an email, and that concludes it for this particular podcast. And join me in the next one. Until next time.